We are live. Hello, everybody. Welcome to the Latin American webinar on physics cycles. Today we have a very interesting talk because it's a colloquium. The colloquium is going to be given by the Professor Sascha Caron from the Radboud University and Nikhef in Netherlands. So just to remind to the people that are watching us via YouTube that all the questions for Sasha is gonna be, you can write it in the chat of the live transmission. Then at the end of the talk, we're gonna address those questions and give the questions to Sasha to answer that. So about our guest, the speaker of today's colloquium, Sascha Caron, he works at the interface of fundamental physics and data science and artificial intelligence. He's involved in experiments, or he was involved in experiments like D0 and H1 and made leading contribution to the dark energy and supersymmetry searches at the Atlas experiment at the Large Hadron Collider. Also pioneering data-driven method and machine learning for new discoveries in physics, leading research in dark matter phenomenology, astroparticle physics, and astrophysics for the point of more research-like. And he had led the initiative regarding to AI projects, including the Dark Machine Initiative, and currently leads a AI infrastructure group for nuclear particle and astroparticle physics, the GENA initiative, and main initiator of the management board member at the European Collaboration for AI in Fundamental Physics, EuCAIF. So welcome at the talk of I forgot the title of the colloquium is Large Physics Model at EuCAIF AI as the new scientific tools. Welcome, Sasha, to lawphysics, and you can share a screen and start your colloquium. We are very interested to hear you.
Oh, yeah. Thanks a lot for having me here and for the kind words and nice introduction. Let me have a look if I can find the PowerPoint slides. Try to start this thing. Can you see the slides now?
Yes, we can see your PowerPoint. Now we can see your full screen. Yes.
Yeah, so my talk is about large physics models and EuCAIF. So what EuCAIF is European Coalition for AI in Fundamental Physics. So I'm going to say a little bit about both topics, and they are also connected. And subtitle is AI as a new scientific instrument. So this little person here who is giving the talk, I thought I'd start a bit with a joke because I've given a similar talk last week at a CERN Colloquium, and now it's on YouTube. So this has been, of course, a generated picture. And last week I had a similar one for the CERN Colloquium, and you can see here how good this works nowadays. So after having these funny pictures, and yeah, there you could also, of course, translate AI as not only as artificial intelligence, but also as alien intelligence. So my son preferred this little alien here in different versions of this plot. So let me start with who I am. I was already introduced, but let's say a few words from my side. So I'm working on the search for signals of new physics, and I do this already since 20 years. And yeah, my expertise or my interest lies in automation, data analysis, data science, and AI. So I tried always to see, can we automatize the search for new physics somehow? Also, given that we have so many different possible signals available. And AI is, of course, there a new tool of making these things possible. In addition, my aim is to see if how we can establish machine learning AI in fundamental physics at large scale somehow. And I will come to that. I think you will understand what I mean with this at the end of the talk. So the outline of the talk is I have a few introduction slides on AI and high energy physics. I talk a little bit about foundation models. What is this and why is this an interesting development? How can that bring us to high energy physics to the next level, probably? Then I move on to text-based models and benchmarking. And combining both brings us to large physics models. And we hope that EuCAIF, which is an initiative, can maybe play a role in seeing how we can actually go to such large-scale models. yeah, I apologize already to a couple of my colleagues and my PhD students that I'm not going to show all the work we are working on. It's just like too broad. And also, sorry for not mentioning your work or your paper if you see this YouTube video. I made, of course, personal selection. So, fun fact, I looked up just before last week for the talk what has been done at the very beginning on AI in high energy physics, and I found actually that there have been, of course, lots of AI papers, but not much things who had AI in the title. And it happens to be that our own work is one of the earliest publications which happened to have AI in the title of a particle physics publication. So this was 2016, where we actually developed a tool called SUSY AI, which was a tool where you could, in principle, put the SUSY parameters, so the supersymmetric model parameters, and there are in most general model many of them, let's say 19 or so, and you could then put those parameters to particular values, and then the tool just produced an estimate if such a model has been excluded or not, given the limits and the searches at the Large Hadron Collider. This was done with 300,000 points as training data, which has been just become available by the Atlas experiment a little bit earlier. Yeah, okay, so just start with large-scale overview. So this is, of course, the famous summary slide on the standard model particles we have as building blocks for our universe. And when you are listening to this talk, you probably know all of this already. But just to remind, we have this beautiful theory, standard model, to describe our small-scale physics. And we have not seen many. I mean, we have more or less a complete picture now after discovering the Higgs boson. So then, large scale, there's gravity, and this is described by another beautiful theory, general relativity with curvatures of space, time. However, we know, although we have these beautiful theories, that this is all wrong. What I mean with all wrong, it cannot describe the full universe. There are still these questions like, why do we have more matter than antimatter in the universe? What is dark matter? What is dark energy? What is general relativity actually doing at the quantum level? And I mainly actually worked on dark matter and did not do anything actually on dark energy. So there must be something missing, and maybe you could think, okay, we need probably bigger machines, a new collider, the future circular collider, and things like this. New machines and new data instruments at CERN, but maybe we don't just need more data. We might also need better ideas. So it could be that we are somehow limited in our own idea space, and it could be that AI could be a tool to help us generate, test, or organize such ideas. So on this slide, I'd like to show you a little bit like how AI is going from initial tools which we have used like 10 years ago to what we have now. So I see this in the line of BDTs, like the Buddhist decision trees, which in the high energy physics world has been used in order to find, for example, the Higgs boson and to train signal against background. I mean, then in about 2015, on the particle physics timescale, deep learning arrived and people were looking into deep networks. We had then a few years later, maybe 2018, generative models. Recently, 2024, people were looking into larger models, more multi-purpose, called foundation models. And last year, we have written then a paper on something which is even larger, which we called large physics models. So let's go a little bit and discuss this timescale. So I have this here in another version. Here in black, you can see a timescale of AI and machine learning, with some developments important, starting with the perceptron, upfield networks, backpropagation, convolutional neural network, then mentioning the term deep learning, generative models, transformers, and then ChatGPT around 2022. In green, I have developments in particle physics here, especially. So we had 1919 already a first workshop on AI in high energy and nuclear physics called AI HENP. And there's then, at some point, we had a development called a toolkit called TMVA, which was a tool in the particle physics analysis package root, which is still had a good implementation of boosted decision trees, and it was most people were using at the time. We had then first deep learning papers around a few years later, 2014. A working group on machine learning started at CERN. Then we had a particle transformer, so a version of the original transformer model in 2017, arriving 5 years later. And it also brings us a bit to the future, where we may have new machines, a new collider, future circular collider maybe, or maybe a muon collider. And then there will be, of course, some AI. What is the AI in 2040, which we are actually using to analyze that data? So this is a plot showing a little bit where AI and machine learning is, deep learning is in high energy physics this year, 2025. Showing a bit the pipeline of particle physics, where you start with producing matrix elements here. You start producing collisions where you have protons colliding with parton densities, with quarks, calculating matrix elements, having some kind of probabilistic process to go to parton showers and hadronization. These particle showers, which are then produced, are put into the detector, and this is simulated via complicated detector simulation. And then at the very end, these particles are then all reconstructed, and you get a list of energy and angles typically of reconstructed particles. In this huge software package, which you could maybe already call a foundation model, but which is mainly handwritten code, which is physics driven and has implemented physics formulas. They're all kind of trainable deep networks nowadays already, and they're at many different places. So you might have many, or it's developed already, some models for the event generation doing initial distributions here. You have models for detector simulation. There are models developed for tracking. There are models, so where tracking is saying which detector information is actually connected to each other. Forecasting flight path of particles like this. Yeah, you go to the reconstruction of those particles. So is this a muon or an electron or so on? And then you are asking inference questions. You do statistical inference. What kind of event is this actually? And you try to unfold the data to get rid of detector effects. So there's a lot of AI everywhere, and it is also AI on the trigger level already, saying us if we should have an event recorded or not. Typically, these are all developments done by different groups and by different people, and they are not really connected. So, but it brings us already quite good achievements. If you just see what deep learning has brought to us in this plot here on the upper right, you can see the background rejection for a certain signal efficiency for top tagging. So selecting top events out of background. And what you can see is here that different models, better models, more complicated models which included more physics and which included better structures in the network architectures, brought us from a factor 500 in background reduction to a factor 3000 in background reduction just in the last 8 years or so. Similar is true in this plot, which is made by the Atlas experiment. You can see the year of the employment of a certain tagger, where this is a network typically which is distinguishing jets from a particular quark type, like B jets or C jets, from light jets, which you consider here as background. And what you can see is also here, starting with the first reference, the first deep learning package, this was already outperforming tools we had before. There is also here a huge rise, bringing us in another factor of 6 in background reduction. So AI is doing already quite a lot, and there is also everywhere in the pipeline. So we have also AI in accelerator optimization in Monte Carlo sampling. I said already, for experimental design and anomaly detection, all kind of things, right? However, so how do we go from this year 2025, where we are now, to 2035? And what are we going to have in 2035? Maybe in 2035, it could look like this. This is just like on one big network, which is a representation of something which is maybe different and where there is more AI in the analysis chain, probably not all AI. That is probably not what, so not only networks, but also still connected, a hybrid probably of physics written code and trainable, adjustable code. So this you could say as some kind of a large foundation model, which AI is included there. You would like that this thing is probably not a black box, but more interpretable white box thing. Somehow this needs to have an interface to humans. You would like probably to talk to your data via a large language model. And you might also, of course, ask the question, how much is this such a tool? How much would that bring us additional performance on what we have already now? And how would we get there? So next steps. Let me just, sorry, I was just skipping over a slide. So we are now seeing in that this kind of pipelines is becoming something which is end-to-end differentiable, also end-to-end optimizable. You could think of something like all parameters optimized now for die-Higgs production or something like that in your full analysis chain. That's something we are not doing now, but maybe we want to get there, and that will bring us additional performance. And you might also have some kind of an AI surrogate model for your simulation and differentiable reconstruction, having full learnability. So, and then what is if this entire physics analysis pipeline becomes trainable, and could AI help us to uncover things we are actually, we aren't even looking for, so finding an anomaly which we haven't looked at yet in the data. So meanwhile, there's of course lots of things happening in industry. So this plot here shows you now as a year of the deployment, different large-scale AI models, which we had in industry, deployed in industry. So like starting here with a GPT-3 around pre-2022, up to now newest version here. And then what you can see here on this vertical scale is the score it does on a famous MMLU benchmark, which consists of many 15,000 multiple choice questions. And you can see that the models get better. They are also reaching already some kind of human expert level on that particular benchmark, of course, over time. So, and on this slide, I like to show a little bit like the performance of different tasks. It's not only that they can answer these questions, and they can also become multimodal. So you see that this first line here, which crossed this human baseline earliest, was image classification. But now we have also recent developments where tools are becoming competitive. For example, in math skills, which is this line here, which in this baseline crossed human performance in 2023, or just recently in complicated reasoning activities. So the models are getting better. You might ask, okay, what about science? Do we have models of science? What about academia? And in this plot here from the AI index report, this is actually they subdivide mentionable models, notable AI models by sector. What you can see here is there is a large number of notable AI sector in industry. So they counted about 55 here in their 2024 count. And then there are a few industry academia collaborations. I may mention later on a few of them. There's industry government collaboration, but there is nothing. There are no models yet in academia. So academia is not producing, you are not getting into these AI, large-scale AI models. And of course, one of the questions I would like to ask in this presentation is why and shouldn't we? So talking about science foundation models and large-scale AI models, I asked last week when I made this slide here, making a deep search in GPT-4o because I wasn't able to actually find out all kind of models, to just list me the 10 most important models and for different domains, modalities, having what kind of data is that trained on, what is meant here with modalities, if they're multi-purpose, if they're foundation-like, and if they have industry partners, and when they have been released. So I checked a few of them. This list is GPT-4o generated, but it seems to be pretty correct, I have to say. So, and you see here, there are some models. Famous one is, of course, AlphaFold. But most of those models are either not completely foundational. And yes, you can see that all of them have industry partners, ranging from Google DeepMind to NVIDIA for Modulus, which is a physics models for differential equations. And they all have some industry development. There's no model, I'm not really aware of such a large-scale model, which we have for fundamental physics. So, which means like this colloquium is about particle physics, astroparticle physics, astrophysics. So how would we get there? And maybe do we want to get there? That was something we asked us a few years ago. And I'm going to try to discuss this further now in the coming minutes. So maybe we should first look at what is the foundation model. So you could see that a foundation model is something which is more general, some kind of a general AI intelligence for a specific, but still for a specific task. So let's say for particle physics or something like that. So but it's trained not only on one data set, but on a large, diverse data set. So you might think of putting this there in general, training it with text, code, images, math diagrams, structured data. So what would it be for physics, for example? You could train this model with maybe your simulation output, with your detector raw data, with your constructed level data, with your analysis level data. But you might also train it with papers, your paper outputs for physics, your plots, logbooks, metadata, such that it understands, gets a general feeling of all these particular things and how they are actually connected to each other. So how would you train them? You would train them in a way which is typically now termed self-supervised. So it's not supervised where you have labels, or it says like this is a cat or this is a dog, and it's also not unsupervised, something which we are doing a lot with particle physics, where you would say, okay, I forget about all labels, I try to learn a general representation of my data. But in self-supervised, you are typically destroying your data in one way or the other, and then trying to restore the data. So at least that is how I understand this whole thing. So what you do is, for example, you have a lot of tokens, you had a lot of text, and you are predicting the next token, or you mask out a certain region of your data, and then you try to restore it, or you can do this with showing it contrastive pairs and trying to learn this then in the model. So in addition, foundation models have a couple of other features typically. So one is transfer learning, which means there's a minimal there is some kind of a minimal fine-tuning needed to go from one task to another task. They are large, they have many parameters, they are multi-purpose, so they can do more than one thing. You would not have like one model just only making, for example, in this doing the top tagging, but the model could also maybe do other things, in your detector, so maybe top jet reconstruction or things like this. And there might be some capabilities which a model could then do, which are not explicitly included during training. Think of a model which learns that certain patterns in your detector are actually connected because a typical particle flies through all of them without telling it explicitly that that's the case. So maybe the model could learn track reconstruction without actually learning track reconstruction explicitly. So let's talk a little bit about these tokens, because token is not a thing which is not typically used a lot in particle physics language. So what is a token? So a token is, you could see that as a discrete information unit, a discrete unit which the model can understand. So typically, if your machine learning model has as input something like hello world, so words, then you could just like, you have to break down in sub tokens. So there would be one token hello or a token word, for example. You can also do similar things with mathematics or with numbers, which could be tokens, or with you could break up verbs, so words, tokens don't have to be words, they can also be just like parts of words, things like that. So what can be tokens in physics, right? So, and can we use tokens in physics? So a typical token comes with a dictionary, a vocabulary, which means that these are all tokens you can make, all discrete units in order to describe your information. So in our world in physics, you could think of having like 10K or 100K tokens, which are describing then all of your detector, for example. I will just show you later on an example where we have used this concept for particle physics tracking. trackings. So, and then, as I said, tokens in physics, they can represent discrete units of information in experimental or in simulated data, and they can be explicit, so either human-defined. I could say a token is, for example, a certain object, like an electron with a certain energy between 5 GeV and 10 GeV, and then there is another token for electrons between 10 GeV and 15 GeV, and so on. But it could also be learned. There are tools in order to learn optimized ways of tokenization your data, and that could also be done in a latent space, or in some kind of an embedding which a machine learning model actually makes. And there are tools like these vector quantized variational autoencoders, which have been used by some groups for applications already recently. So as said, so examples could be detector components, identifiers, channel models, layers, or bin versions of things like jets, tracks, etc. So let's walk us a little bit through a setup which we could use in order to build a foundation model. So typically such setups comes with a structure which is an encoder-decoder architecture. So an encoder and decoder would be both, you could see this as neural networks, where you would start with some input tokens, your input data, then the encoder would actually put this into some kind of a latent vector representation. And the decoder would then go from that representation and could produce then, for example, the next output token, the next word. So, and as an example, let's assume the input would be the Higgs decays 2. And then this sentence would be tokenized to these tokens, the Higgs decays 2. And these tokens, they would then become numbers, because the network can only produce, can only do something with numbers, right? So let's assume that you would number your token, and the token would be in token number 45, Higgs would be token 1293, decays would be token 34, 255. Typically, then there is a vectorization step where you then actually go to a larger embedding, and then this maybe 64-dimensional or whatever, and then this 45 would be replaced by a large-scale vector, or vector 45 in the model, and this would be then processed further as input in your encoder neural network. So let's have a look on the right side on the output. So how do we actually get the output token? This is typically done such that the model predicts a probability output, so derived by a function like softmax, such that they all normalize to 1 over all your dictionary. And you could then take the one with the largest probability, so the argmax over all the probabilities, or you can sample from that probability distribution, which is typically done in the language models in order to have more natural language. So if you don't do that and take the argmax, then ChatGPT would just sound a bit robotic to you. So that's an example. So it could be that our output tokens examples would be BB bar, Higgs, hello, and Susie. And then the largest probability would be BB bar, the Higgs decays to BB bar. It could also maybe decay to Higgs, so therefore there's all probability is not 0. So the model thinks, there is also some probability. And it has probably read too many papers on the archive, so thinks Susie could also be some kind of a decay probability because of the symmetric model. Okay, so typical architectures to do such an encoder-decoder historically are things like recurrent neural networks, RNNs, where you have then this input in here, x1, x2, x3, and then you are producing some output. And in this case, there would be just one output, y1, produced, which would then be your probability vector over all your different tokens. So such models like RNNs, they have a bit of a problem, which is this bottleneck. So all the information of all your input has to be stored in one so-called hidden vector over here, before it actually produces this output. This is seen as a problem in the machine learning. So it cannot actually process all that information of all these inputs. So it's too much information somehow here. It might also probably need these hidden vectors, which it has produced from the other inputs. So then there is a thing which came to rescue in machine learning, which is so-called attention, which actually allows us to attend your output to certain information in your input. So this attention was then brought further by the Attention is All You Need paper with the transformer architectures in 2007, which replaced this bottleneck somehow with a thing which is called self-attention. And this self-attention is building a correlation matrix of your sequence to your sequence, self-correlation matrix. And in the self-correlation matrix, one can actually also put in physics there to tell you how this thing is actually correlated, and that actually helps in getting better models. So in addition, we have this latent representations, which is over here, which is still there and which is also important in these foundation models when you replace now these RNN decoders with transformer architectures, which people are using right now. So typically now, these recent papers, they are using an input and then they have an encoder transformer self-attention layer, plus some vector quantization layer, which learns these tokens, yeah, and produces a codebook, a dictionary of tokens, which is learned. And then you get a quantized latent vector representation. So a quantized version of your data, which is more or less optimized to a smaller dimensionality typically. And from that set of numbers, you are then with a decoder producing the tokens, the output tokens again. So here's an example of how such architectures work. So there was many attempts on EuCAIF on this foundation model ideas in 2024. And then I just show as an example a tool called OmniJet Alpha, which has been used for jet physics here. This is just like here for an example where you see here these things again back here. There's a transformer backbone. It does some next token prediction here. And there is a vector, this quantization variational autoencoder architecture again. And it actually makes also some kind of an embedding of tokens. So you see these different colors are like different tokens, different discrete objects, particles inside your latent space representations of your jets. And then this thing can do the multiple things. It can do jet generation. It could also do jet classification in a sense by using a different head, a different output network. So the next slides are some very personal selection of things, showing a bit as an example what my own group is doing towards foundation models in higher energy physics, with a similar idea behind that. So what we are looking at is we would like to start with the very earliest you can think of in this particle physics reconstruction pipeline, and this is with the raw data. So what is the raw? This is a typical picture of an event you can see at the Large Hadron Collider. You can see these colored lines here, and these are actually particle trajectories called tracks. Right, you can see that they build different vertices here, and one big task is a computational challenge is to reconstruct those tracks from hits which we have, so detector sensor information in our inner detectors. So how does that work here? So it works here that our inputs are now those hits. There are many of those. And we have an encoder. We have this again, the same model, a latent vector representation, a decoder, and output. And what we tried in a recent paper was that we are using different strategies. One was we tried to do full translation, so going from hits to track tokens. But we also tried regression strategies, so more traditional, where we did start from the hits to actually track parameters, which we then clustered here in the output space. We also did some kind of a ChatGPT type of version where you have to predict the next word, but and it is worked also pretty well. We used here some similar architectures here as we had in the original transformer paper with an encoder-decoder type of model. However, with such models, they don't scale very well because you have to predict, you have to ask the model every time, what is the next hit, what's the next hit, what's the next hit, what's the next hit for every track. And that means you have lots of time to actually build autoregressively. That's how it's called, right? Predicting the next word or guessing the next hit, such a full track. But you can see it actually works. So all the three models we have built works, also the autoregressive ones. And it can here with our example data actually find the track curvature and just can predict the next hit as it would predict the next word in ChatGPT. So let's have a look again at these tokens here. So our input are here, it's TrackML data, and we are having an encoder structure and then we have a latent vector representation. And in that latent vector representation, the hits which are belonging together, they are grouped together. They have similar parameters. then the decoder takes them in from the vector, from this latent space and produces outputs. And these outputs are now track tokens. So in our case, the tracks are actually discretized, similar as we did many years ago, actually in an experiment where I was involved in Fermilab. It's called D0, where we actually had so-called roads, which were just like, we had a discrete version of possible tracks. So a track which has a certain PT range and a certain phi range and a certain theta range, they are actually becoming then get the same token. And the output is now a probability for each of those detector information over all these different tokens. So that means you get a full posterior as output. There is not like that you only have one particular, that every hit is associated to one track, but what you can see here in this color code, these are just like plots for 5 different hits, is that this green hit here has a probability to belong to that track, but it has also some kind of a probability to belong to this one, which is very different, at a different, has at least a different token ID. So we get a full probabilistic model with that, which might be a cool thing to have. So remember, when we do this, we have about 10 to the power 5 input hits, 10,000 sequence, 10,000 long sequence, and our output is typically a factor, is about 1,000 tracks. So we go from 10,000 to 1,000 with one model, and the model is pretty fast in doing that. Depending on what kind of GPU card you can do this and how you're actually trained the whole thing, this thing might work in several milliseconds in doing that, getting that output here. So how good does such a model work? And here you can see a couple of plots. You see that our tokenized model has quite good fit accuracy, actually. And another thing which I like to show you here is actually that the training data, we are using TrackML challenge training data, which is public available, is not enough to make the ultimate performance of the model. So if you see here, this is a plot showing you the validation loss as a function of the epochs. And you can see that the model is still improving. It wants to have just, and this is just like, not the epoch, sorry, it's a fraction of how much training data we're actually using. So which this is full training data, and this is fractions of training data. And what it then shows is, I would like to have more training data, because then the model would even get better, but we just don't have this data public available right now. So as said, we are training 10 to the power 4 to 10 to the power 3, but you could think of having such a similar model now being in place, which actually goes to high-level objects like jets, electrons, muons, and so on. So this is 10 to the power of 2. So you see that this problem is the same scale. It's probably an easier problem when you have solved the 10 to the power 4 to 10 to the power 3 problem. Then going from 10 to the power 3 to 10 to the power 2 is in principle possible, I believe, even though it has not been shown yet. Finally, we could just go to 1, where 1 would be just like a binary classification output. Is this an Higgs event or is this no Higgs event? Is it signal or is it background? And that is something like, then you would have a full end-to-end AI pipeline starting from the raw data and just going all the way to your Higgs. Is this an event in a Higgs or no Higgs? So that comes, of course, with challenges. So you are losing all interpretability. That this is a completely deep learned black box model, which you don't want to have. You would like to have some control. You would like to have uncertainty estimations, etc. So at some places, we probably have to find out how can we make such a model which is at the same time has probably is interpretable, and we have to find out what is the performance of such a model. Are we actually winning, and how much are we winning compared to what we have now? So there might be a need for a flexible and interpretable model. So having discussed a bit the data, the detector data, and foundation models on those detector data and particle data, we might look at different modalities. So modalities, I just took that from the IBM webpage, is something in this foundation model, large-scale AI model, are just like your different data sets you're looking at. So modalities in particle physics might be text or in detector data, simulation, math data, your formulas, plots, and of course also code, because that's probably one part of the language in physics is code. So let's have a look at some other modalities, and if we could actually implement them as well into AI models. So next thing is text and code. So when you think about larger models, larger AI models for fundamental physics, text is of course important thing to look at, and we could of course want to have a model which is trained on text and which has probably read all our paper we have written on the archive. So if you look at these text-based models, there have been some already proposed, and there have been in recent years, in the last 2 years or so, language models, large language models for physics, for fundamental physics. But it typically come in 2 categories. One is using retrieval augmented generation, called RAG. And what that means is they are just using models like GPT-4 or GPT-3 or whatever kind of commercial tool, and they're inserting their additional information, like Atlas internal information, into the text, into the input prompt. And this led to a model like the ChatGPT, where I have a slide over here. Another possibility is to actually change your weight. You start training a model like Llama 2, and then you are fine-tuning that model to specific domain applications. So this has been done for astrophysics in the AstroLlama paper, and they claim, I think, in this paper that it actually has some kind of another better understanding of Llama, of astronomy, and can make better abstracts than the original model. So, of course, we want to get further, and that brings us to the question, how are we going to benchmark this development? How good are those models? And having asked that question, you might think, how do these models actually have some kind of a scientific understanding, physics understanding, and is this actually a relevant question for us? So that brought us, in my group here at our university, to the question, what is actually scientific understanding? And in our house, we have actually a philosopher of science who is working on understanding scientific understanding. And together with him, Henk de Recht, we had a look and discussed a little bit, like starting in 2023, so already just before ChatGPT came out, about how could we actually benchmark, or how could we actually measure scientific understanding in AI models and in humans. And in philosophy of science, it seemed to be that scientific understanding was some kind of an internal mental state. It was more binary. You either have it or you don't have it. And instead of presupposing such an internal mental state and representation, so we suggested in a paper then that we needed to that understanding is something where we can identify with an agent's ability to reason about and manipulate objects of investigation. And then understanding is not binary. You can actually have a score associated to this one. So then you could ask, how do you test that? You could ask that with different understanding of physics. So to what degree does ChatGPT understand the behavior of a simple pendulum? How are we going to test that? You can just make all kinds of what, why, and counterfactual questions. For example, what is happening if the pendulum is on Mars? What's happening if the pendulum is on the water? What can you calculate this and this and this? And by that, so similar as we do in students' exams, we would grasp the understanding of a model, of an AI model, on such an object like a pendulum. So then if such a benchmark is measurable, we can associate a score to that. So starting from no understanding, a score of 0, to some average expert understanding of scientific committees. You could go above that, having maybe an understanding of all of us together, the particle physics community. And if you would have in some question, an understanding which is above that, then maybe that would lead to a new scientific understanding, and that would maybe be a discovery of something new, something we haven't understood before. Yeah, and comes also with the question, who's responsible for monitoring AI scientific understanding in fundamental physics? Should we, the fundamental physics community, the particle physics and the astrophysics and the astronomers, should we not also have a say in that? Should we not take the lead? I mean, we had a workshop on this, and I'm discussing a little bit benchmarking here idea. I'd like to show you just an interesting benchmark which has been recently proposed, which has an interesting name called Humanity's Last Exam. And in that benchmark, top system score just 8% or so of the questions correctly, as only 8% accuracy here, as you can see in that plot. And there's also something called frontier math, a complex math AI, and there were also only 2% of the problems were initially solved. So we were thinking of building something similar already in that workshop for physics. So for particle physics. So, and we are working on a benchmark for particle physics, which has 3 times of questions. We would like to go for difficult and deep questions. One is questions like ABCD questions. So we have I give you a question and you have 4 correct answers. Which one is 1 correct answer and 3 are incorrect? And the question is, of course, which one is the correct one? Instead of giving the model only the correct questions, giving a correct answer, you might want to have open-end questions. So something like, what is the result of X, Y, Z? And the answer would be, let's say, something like MC squared without knowing it, or 2MC squared. And there's a third category, which comes with things like programming exercises and things like that, where the model comes with a score, and a higher score is better. Yeah, we have a webpage here, physicsbenchmark.org, and if you would like to propose a question, just send a mail to me or Eugene, who has set up this webpage, and you can get an access token, and we can try to collect with these questions and make them hopefully available to the public via paper soon. So here is just like an interesting example. So here we have asked different models to select 4 top events, a particular type of signal against background, and to write code for it. So it's a coding example. And you can see here the performance of Anthropic, Claude, DeepSeek, and Google Gemini as a function of the training epochs. You can see that they are doing differently good. Some are doing better tricks than other models. And with this, some models, most of them, they actually don't solve that exercise at all. They currently have an accuracy of only 0.5 because they are not able to write code which can actually do this. So this brings me to this large physics models, which was a reason of this seminar, and what we started 40 minutes ago. And this is like a large-scale AI foundation model, and we would ask the question, what would a large-scale AI foundation model actually look like if it were actually built for fundamental physics? We have worked on that also as a result of the workshop, and with a couple of people from EuCAIF, written a paper on it, which we recently released on EuCAIF, where we discussed about this. This is also a collaboration with philosophy of science people. So what is a large physics model? So this is inspired by ChatGPT-like foundation models, so like LLMs, vision models, multimodal models, and the LPMs are actually models that are trained natively on physics data, structure, and tasks. And in addition, they are under the control of the science community. That's also part of the vision, right? That we know what the models have been trained on, that we actually train a model, that we have full say of it, that this becomes an AI for us, for the science community. And it should go beyond chatbots. It should integrate symbolic reasoning, simulation, mathematics, data-driven inference via links to physics raw data, and so on. So you have all these kind of modalities here, physics reasoning abilities, and there is a human, hopefully, in the controls there, and using and interacting with these large physics models, producing physics output. So in a paper, we have seen it similar to this. There is a conversational AI, a language model here, which has an interface to the humans, of course. And then there are foundation models for particle physics, which is actually able to run particle physics data analysis simulation pipeline, has access to data. And something similar is then there for gravitational waves, or astrophysics. So that's such that the model can actually orchestrate all these different models and could also connect via doing that different domains. So there are 3 pillars which we are investigated for the large physics models. One is development, more what I said on there. So there needs to be a multimodal model with symbolic and numerical code and data input. But there needs also to be evaluation. So we need to have these deep scientific benchmarks that reflect on physical reasoning, which have to be developed, which we don't have yet, so at least not in the particle physics and fundamental physics community. And there needs to be philosophy of science there, because there needs to be some kind of a reflection, I believe, on what it means for an AI to understand or discover. There needs to be a reflection on human AI intersection, because that's a new thing, a new area we are going in, and they're coming with ethical questions and of course questions on who's controlling this thing at the end. So these large physics models, LPMs, they need a new kind of collaboration. So how is it possible to do this? This is not being built by me alone or by any group on Earth alone. We need to have build a scientific infrastructure if we want to go there. So, and we in our paper, we think that with this, requires a collaboration between these physicists, computer scientists, philosophers of science, maybe industry partners. And that such a collaboration, they could be inspired by collaborative structures we have already now in high energy physics experiments. Like Atlas on CMS, it consists of 3,000 people, and they are multi-billion-dollar endeavors made for science, and they work. Could we build such a thing, maybe initially on a small scale, to build large physics models? So how can we get there? Yeah, so a roadmap would be, we would first be in a phase 1, which is a physics native benchmarks and tokenization strategies, building prototypes on simulation text and code, larger and larger prototypes. I would see that as phase 1 and phase 2, and maybe we are now somewhere in the middle. And then there must be a phase, probably, to have general purpose models that assist theory analysis simulation, and that needs a structure. And that the question is, how can we get to phase 3 now to have such a structure? Yeah, on this slide, I'm not going, you can just pause the video and read this. I've listed here a little bit like pros and cons from the paper about, you could think like, are we going to do it? Should we build LPMs? Should we not do LPMs? There's of course a risk of that of arrival. It could be absolute before completion. It could be less useful as we actually have. It could be hyped and so on. On the other side, there is of course lots of pros. Yeah, it can do better things. It can help us doing the next discovery. And maybe if you think about that and how science is going to be done in 20, 30 years from now, you might ask yourself the question: should we have a scientific physics AI, and who is going to build it if it's not the scientific community? Also, industry versus science is, of course, a question. So you have seen when I talked about these foundation model examples at the beginning that in all of them, industry has some connection. So you could think of having some kind of a collaboration with industry, and that could be a win-win, maybe. However, science should have its own goals and define the goals, the structures, and the values, we believe. So then on that last slide here on these foundation models, I'm thinking about feasibility. So what would be needed to this? So we did some guessing, right? You can only do guessing at this stage, I think. So in Europe, people are planning AI gigafactories. So these are like 300 million euros or something like that factories. And maybe you could think of having something like access to about 10% of such an AI factory at the beginning. So not a gigafactory, but an AI factory to train such a model. You might need about 100 staff scientists, postdocs, PhDs dedicated to such a problem. And the costs of such a thing would be a cost of maybe a small size particle physics experiment. So potentially, you could see as LPM, so large physics model, as a computational experiment for fundamental physics. This may be a new thing, and it would be a flagship project combining AI, theory, simulation, and data in a shared model infrastructure for fundamental physics. Yeah, if you look now 10 to 20 years into the future, as I said, there will be many tasks that have been done by such an AI. And you might ask the question, should science have control over these models? And for this talk, I asked ChatGPT, what should we do? Should we, yes, say we build large physics models, train them openly, shape them around physics, or B, use general purpose tools, depend on opaque systems? And guess what? What do you think ChatGPT has answered? It just says, what? Yes. You know, what's your opinion? Yes, the scientific community should absolutely build large physics models, no matter what. This is a great idea, grounded in strategic perspective, and there comes a lot of reasons why you should do it. However, you have to ask questions, final thought two here. Should we really ask the AI for questions about more AI? Who is going to ask the scientific questions at the end? I mean, we have to keep control still, right? So also this talk, I made this talk, but I consulted an AI on a couple of things here for this talk. We should not rely too much on it. And maybe that comes also with the reason on control, if we build our own models. Okay, so that's the end of this large physics talk. And asking the question, how can we build to this large community, having a community effort to have AI? In Europe, we have built up a coalition 3 years ago, which is the so-called European Coalition for AI and Fundamental Physics. And with that coalition, we we are trying to influence politics a little bit, European strategy. I have to say, maybe I shouldn't say openly on YouTube, but we to the event. So EuCAIF as a structure with a management board and fellows, which are staff members, an international advisory board, and some members, and we have also working groups. And working groups, one of them is Working Group 1, which is about foundation models and discovery. And this group is, of course, at the heart of this talk here. This group is chaired currently by Tobias Golling and Lukas Heinrich. You can contact them if you're interested in this work. But we have also other working groups, for example, on fairness and sustainability, and strategic working groups. So this is a slide of these foundation model working groups. I think I've discussed this already. So for these large-scale models, one of the things you can think of LHC would be learning some generalized embedding, which you can then use for multi-purpose tasks, and see how far we can get with this. This is a list of names we have on EuCAIF. You can pause. This is just like the version which from last week. We have now already a couple of new members. And if you would like to join the activities, you can send a mail. You can also go to the webpage, www.eucaif.org. And you can also request a membership if you would like to join us. We have now junior fellows as well. So this is for experienced postdocs working in AI and fundamental physics. So also if you have not a staff position, so all those people who are listed, they are actually permanent already. You can become a junior fellow and help us shape for Europe this AI in fundamental physics structure. We said we have this conference series. Next one is in Sardinia. There was one last year in Amsterdam with 250 people being there in person. And we had lots of talks also with industry partners who gave talks, interesting talks there. And we produced some output. 3 papers from EuCAIF now, just on this year written. One is a strategic white paper on AI infrastructure for particle, nuclear, and astroparticle physics. This is some input to the European strategy for particle physics, which is happening this year. So what's the future of particle physics? What should be our recommendations? What we should build next? And we have written some recommendations in this paper here on AI, which you can see on this slide. You can just pause and read if you want, if you don't want to read this paper, but I'm not going to do this now in a YouTube colloquium. It's much too boring. Also, you don't want to listen to me the whole night. So there is another paper together with Jena, which is a joint ECFA, NUPEC, and APEC group activities. And so here we have submitted something to the European strategies as input. And we have written a paper where we have also to the European strategy as input, where we proposed so-called AIRDs, AI research and development groups, which can help us to work on specific AI topics in fundamental physics together. And I do think time is up. We have about 57 minutes according to my time. So I just want to close with saying you can still register until 31st of May for this conference we have in Cagliari and beautiful Sardinia. And you can join us there and discuss with us if you are interested in AI and fundamental physics. And this is my very last slide, where I like to summarize. I think you have seen that the integration of the large language models into scientific research is not only likely, it is already ongoing. We propose a concept called LPMs, so large physics models, and they are not just about better models, they are also about scientific sovereignty. So sovereignty for us as science community. However, as I said already, we need to be careful. The science community needs to have control. We need to be careful in this process. We need to keep control over science and also our own thoughts. And maybe having our own model is probably the way to do that. And in Europe, EuCAIF is the first step towards a European coalition in AI and fundamental physics. That's it. Thanks a lot for listening.
Thank you very much, Sascha, for the very interesting and nice colloquium on the talk. Um, for the people that are following us in YouTube, you can ask questions to Sasha. We are gonna give them later as soon as they are showing up. But before we can start, maybe with the people here that is in the Zoom session, if they want raise their hands for asking question to. There is a question from Maria Eugenia Cabrera.
Hi, thank you for the talk. That's really nice. I just have a short. I don't know how simple it is, but you say something about the errors in the error estimation in neural networks. So, and also you comment about the evaluation of the knowledge or understanding of the neural network. So I am wondering, shouldn't this be related? I mean, when we say that we don't know how to estimate the errors, when we use a neural network, you train a neural network, you have some result, and you still don't know very well. We don't know very well how to estimate or understand the error. And then you compare it with this measurement of understanding of the neural network, and you compare it with a quiz or exam of a student, something like that. So this shouldn't be related, or this is just something?
Yeah, thanks a lot for the question, Maria. So this is, of course, a super important question. And this is at the heart of what we need to do. So we care more about uncertainties and error propagation and all of that as scientists as the AI community does. So that's also something where we have probably to look at what is available and probably make things better. I think my answer to this, maybe I just can give you a few examples, of course. I mean, there is, of course, this explainable AI movement, and you have all kind of tools, but you see that in these foundation models, if you would have, for example, a full posterior over which detector information belongs to which particle and brings how much information to that particular particle, maybe that is something which we don't have now, because now you typically, this is a discrete thing, a particle is made of this thing, right? And the information that could also belong to a different particle is just ignored in our current pipelines. So it might be that future pipelines can actually help in understanding uncertainty better than by having a full probabilistic model and having a full posterior in between than what we have now. My second answer to this comment would be on the large language models and in general on large-scale AIs. I believe that's the reason why I think that benchmarking should not be underestimated. We really have to see what these models are. Are they just dreaming nonsense about physics and or not? And how good are they actually doing over time? And because more and more people are using them, our students are using them, we are using them, we are using them for code writing, we are using them for whatever as an artificial muse to talk about physics or something like that, ideas. You would like to understand what is their actually understanding. Is it how trustable is this in this particular subfield, and how deep does the knowledge go, right? And maybe you would like that the answers come in the future, maybe with some kind of an uncertainty, which they don't do right now, right? So that would be possible if we would have our own benchmarking, because then we would have more control. But if we would even make our own models, we would also be able to have such an uncertainty embedded and from the start, right? Yeah. But I mean, I don't think that answer, even if it's long, does answer all possible questions one could think. I think it's an important question.
Okay, maybe another question. There are other questions from the people here in Zoom. Otherwise, I have a question from Walter that he has to leave before. So, but he left a question for Sasha. His question is, in what ways is machine learning improving real-time decision making in trigger system at collider like LHC? Kind of.
Yeah. What we are doing at LHC is typically the trigger there's a first trigger level which is more hardware oriented, which has to be run pretty fast. Yeah. Typically, when you subtract that there is some pipelining, I mean, some buffering, you would have to make in the most optimal world a decision with the beam collision frequency, so which is 25 nanoseconds or so of the LHT. And this means you have to run a network on FPGAs. There is no way out, and that means you need to have small models. You cannot work with large models. They need to be dedicated small models to do that. And we are building such things now. There is already, I mean, my group was already a few years ago having a very simple perceptron, which was regressing missing transverse momentum at the LHT at trigger level. That typically works. I mean, we have seen that can work better than not doing that, because you can build small models which outperform simple if clause type of decisions on the trigger level. And people are also working, of course, in anomaly detection. And there's a whole group at CERN now interested in how can we actually put the newest architectures on FPGAs. So, for example, how do we put transformer architectures on FPGAs?
Great. It's very interesting the feedback loop that you can get with the AI. So other question from here, because we have many questions from the YouTube. I mean, there are some that they were talking about other topics like material science, but let's focus on the one related with higher energy physics. There is a question from Halil or Jalil. It is large physics model can affect the fast of simulation calculation, kind of
The speed, I think it
or
meant.
the speed, yeah, the speed of
simulation.
simulation.
I don't think that a large physics model would. I mean, large physics model maybe you would. At the end of the day, you have to figure out first. The first thing when you start a simulation is to decide what are you going to simulate, right? What kind of parameters do I put into my simulation in order to get some output, right? And maybe there having some smart thing which can actually do that better helps. Yeah, there are some known techniques like active learning, for example, where you know from your previous simulations where to simulate the next things. And on the other side, in simulations, I mean, where typically machine learning can help right now already is you have to start with initial random number. I mean, the input is always like random numbers, and those random numbers they have to follow certain distributions, right? So that means and having these random numbers following a better distribution in a complex phase space, sampling better this phase space more efficiently, knowing likelihood that you can already now have tools like in the machine learning world which you can use. So like normalizing flow models and things like that.
Yeah. It is. Yep. Okay. I don't know. We have another question from this name is Sakabato Blood. Maybe it's just the nickname for YouTube. He is asking, or she is asking, how could be sure the imperfection in our theories data / understanding given to an LPM as training data wouldn't be propagated and amplified? It's kind of the typical problem of that usually is referred to other like
I think there is a danger that it is amplified. It could be that the LPM, if the LPM is automatized to a certain extent, so if you know and does multiple steps, right? Many steps. It could be that at the end there is a mistake at the beginning, and then it will just follow a wrong trajectory, and we will lose lots of computing time and resources by following longer this wrong trajectory, and it would probably just generate nonsense events and so on. It's a danger, yeah. I think we have to see how that would be our work. I think there should be a human in the loop. That is maybe a way to control things and just not letting them automatize too much, at least not at the beginning. A human in the loop is always a good idea, I think. A physicist.
That's kind of the supervision for the
Yeah.
Yeah, because it's common in just with the commercial AI that they make mistakes, even though
Yeah,
they are
yeah,
there. Yeah, on one a human can say clearly there is an
yeah.
error here. It remain in the loop.
Yeah,
The error
but you
message.
see, if we would have a model our own, so if we would have some kind of a community large physics models, we could also have a database of mistakes. I mean, if it makes mistakes, we would all feed that database, and by that we would know what are possible pitfalls. Where is the model wrong? What is there? It's not only benchmarking, which is coming, um, where you have then a set of questions, and then you ask the model, how good are you actually in this kind of questions? But you could also, of course, actively say where the model fails, right? And then by that steering it towards becoming better.
Hmm. Yeah. Are there questions more? I mean, I have a question for myself because at some point in your talk, I mean, I guess Joel also has a question. You were talking about the input token and the output token
Yeah,
for the training. Such input token, in principle, they are kind of defined at the beginning by the person that want to to feed to start the the AI model itself, or they can be the same AI can retro create this kind of input token. Because you were talking like, okay, you have a token that is Higgs particle and spin zero, whatever, for that is defining the physics. But maybe there are some input tokens that the human cannot foresee and need kind of later
yeah.
on retro included in the as an input token for the defining the physics model.
Yeah. So if you want to, so first, this tokenization strategy is not like that. You really need this always, right? You could also say, okay, I'm for example in this you could also say, okay, I don't need to have these discrete chunks of data, right? But it's sometimes that this discretization just helps then, because then you say, okay, that is a particular, because you can do train. I mean, one reason why it helps is of course also because you can do all kind of tricks which the language models do nowadays, right? Because they have these discrete chunks of data. And I mean, and how do you make, however, I think also you could just say, maybe having discrete information units is something which is interesting for physics, because we have not looked into that systematically yet, right? We have always some clustering strategies like jet algorithms or these tracks where we say, actually, we would like to have something which is real. We don't want to have like a discrete thing. We want to have a continuous solution, yeah? Um, and I mean, how we can make these tokens, I just showed examples. You can either automatize the making of the tokens, and you can do this in some deep learned way and some latent space where you have no control over what they actually mean, maybe, yeah. But you could also, of course, discretize them by yourself, because you know this is an electron, this is a muon, this is a jet, whatever. We have already discrete entities, and then it would be kind of stupid not to use that knowledge, right? So that means we would have these discretized things already now. And I mean, I see many of the papers from last year as first attempts to find out what is the optimal strategy. What are we are, what are the pros and cons from different strategies in doing this? I think we have not brought this to the end, right? So you was thinking, for example, if you could just like how far could you go with discrete information units?
Yeah, also it make it cheaper for the, I mean, faster for the calculate for the generation and for the energy consumption, I guess, for the training. Yeah.
Yeah, there would be of course faster to produce, right? Because you don't have the I mean, you don't have these steps where you have to cluster your data, right? The clustering algorithms, which takes you times, but they might also open new avenues, right? It could be that I don't know, let's assume you would have jets, and there would be no jets. There would be just like 10,000 different tokens, which are discrete chunks of things. Would it be so worse in understanding physics? You could maybe publish those tokens and compare them to your next leading order calculation or something like that. I don't know, directly. And if they are predefined, maybe that has some advantages. I don't know, because you could maybe also the simulation would be faster or something like that. I don't know. Like maybe you could define them such that they are IRC safe or so. I don't know.
Yeah. No, yeah, it's super interesting, and all the implications, as you said in your colloquium, what is going to be in 2035. Everything, because every week we have newer news about new AI tools for the company, the big companies. And yeah, I don't know how it's yeah, but usually it's just kind of commercial and not applied for high energy physics or astrophysics. So it's like yeah, always trying to be general purpose.
Yeah, we are for them just a spin-off, right? We are just like a side product,
Yeah.
probably. Yes. And still it's pretty powerful, no?
Yeah, I know. And I know many experiment nowadays. Most of the experimental collaboration they are using not AI but AI tools like a neural network for the training of the data, the observables in general, because they're too complex nowadays. For instance, in Dune they are using convolution networks, perceptrons. Now in more related with astrophysics, also for the reconstruction of the showers of cosmic rays in the upper atmosphere. It's crazy how this tool that has many years, a couple of or 3 decades, let's say, is nowadays is kind of becoming a standard for in science.
No.
And how to integrate the Multimodal tool to make it more abroad. That is discover your or colloquium, let's say. I don't know. Are there other questions in YouTube? They are saying to you, "Thanks for the talk. That was very useful." Just to remind also to the people in following YouTube that the video remains in YouTube, so people can watch it again and go to the details on some part if they want to learn more about this, and also if they want to participate of the initiative that the Sasha was saying in the talk about the question for the AI.
Yeah,
Good
just send us
question.
an mail. It's all work in progress, right?
Yeah.
Need to cooperate.
Cool. If there are no more questions, so we can, we thank Sacha for the nice colloquium. Also, I tell to the people to invite them for the next webinar that is gonna be 4th of June. That is gonna be by Adrian Thompson. So just for the people there to stay tuned to Law Physics, and of course again to say the thanks to Sacha for such a nice colloquium. So. Thank you very much. We
Thanks
say
a lot for
goodbye.
organizing this and for the nice words. And yeah, it was really a pleasure. Really cool initiative here. This you're
Thank
doing
you.
this.
Okay. See you all. See you next time.
Have a nice evening or whatever your time zone is.
Midday,
Bye.
noon. Okay. See
Thanks.
you.
See you.
Okay. Se fue.
Ay, se fue.